So we're going to be doing a problem with nuclear decay. So we're going to have an atom of uranium-238, which decays into an atom of thorium-234, and an alpha particle. Alright, so the things that we have to do is find how much energy is released, and what the wavelength of the radiation released is. Or frequency, or wavelength, it doesn't matter. So, to start, we're going to find the mass of one atom of uranium-238, which you can just find online at wolframalpha.com is what I use. So that ends up being 3.95282 times 10 to the negative 25th kilograms. And it's important to do it in kilograms because then you can get a really easy conversion into joules. And it's also important to be very precise because if not, you're not going to get the minute difference in energy that you get out of this reaction. So this is for the uranium, and then for the thorium, the mass is 3.853082. Well, okay, it says uranium and then thorium here. 2 times 10 to the negative 25th kilograms. And then we're going to have the alpha particle, which is going to be 6.646478 times 10 to the negative 27th kilograms. So the two masses on the sides of the reactions are what we are going to compare. So we have mass with uranium-238, and to find the amount of mass lost, we're going to subtract the sum of the masses of both of these particles. So when we add these together, we're going to get a mass of 3.919546678 kilograms. Alright, so, and then we're going to subtract this mass from that. So if we're going to have the uranium-238 minus the thorium-234 plus the alpha particle, that gives us 3.253522 times 10 to the negative 27th kilograms. Alright, so that's the mass that's lost once decay happens. So now we're going to convert mass into joules using E equals mc squared, and the conversion for that happens to be that 1 kilogram is equal to 8.988 times 10 to the 16th joule. So we're going to multiply these two together, and we're going to get the mass lost times 8.988 times 10 to the 16th joules over 1 kilogram. So this mass in kilograms, so the kilograms cancel out, and that leaves us with 2.924265557 times 10 to the negative 10th joules. So it's a really small difference in the energy that we actually get, so that's why we have to make sure that all of the measurements are so precise, because if we don't have that, we'll just end up with 0. Alright, so now we're going to have to convert the energy into wavelength or frequency. So I'm going to erase the part with all the mass and just do that. Alright, so the equation for energy is energy equals Planck's constant times nu, which is frequency. So the energy that we have is 2.924265557 times 10 to the negative 10th joules. And we're going to divide both sides of the equation by Planck's constant to get the frequency. So when we're dividing that by the Planck's constant, which, oh, sorry, give me 1 second, which is 6.626068 times 10 to the negative 34th, that will give us the frequency, which in this case happens to be 4.413274313 times 10 to the 23rd hertz. Okay, so when we have that, we know that gamma rays, so the gamma ray frequency, is usually greater than 10 to the 20th hertz. So because 4 times 10 to the 23rd is greater than 10 to the 20th, we can conclude that the radiation emitted from this decay reaction is in the form of gamma rays, and that this is the wavelength of that radiation.
That's the frequency.
Frequency, sorry.